Hello, I'm very sorry that this lecture is a bit late. It was very hard to make this one. PowerPoint kept crashing, things weren't working, so let's hope this goes well. We move on to functions and ultimately, of course, calculus. So we have already seen functions in this course. If you remember, we saw linear vector functions in lecture B. That was, and if you remember, any matrix, an n by k matrix was a unique representation of a linear vector function from Rk to Rn. Now we go to functions where you may have one x or several x's, but you always have one y. So the big difference is in vector functions, you could have several x's and several y's, whereas now you only have one y and possibly multiple x's. So a function is a rule that tells you that take a number from the domain, the x's, right, and assign a unique number in the range, the y's. So it's really important to note that once you tell me what the domain is, every point in that domain must somehow end up in some point in the range of the y's. If you have one x and one y, it's called univariate function. And if it's many x's and one y, it's called multivariate functions. The thing that makes functions tricky is that they can be given to you either explicitly, as in you literally know y in terms of x's, or implicitly, where there is some relationship that may be given to you in terms of equations, or it may be given as a very high level uh, uh, statement. For example, you could say revenues depend on quantities and price. That could just be a very gentle statement without me having to say what the equation is. So we have to work with explicit functions where you're given y in terms of x, and implicit where it's perhaps not possible to isolate y in terms of x, or you just give a very gentle statement. I'll give examples in a few minutes. As you can imagine, most graduate school, obviously, you're not good. You'll be very lucky if your professor always works with explicit equations. Obviously, most of the time you work with implicit equations. And that's going to make things very, very hard in terms of taking derivatives, differentials, and so forth, which is one of the reasons why this lecture took so long. Here are some examples of explicit univariate functions. 1x going to 1y. So you can look at them at your own leisure, but you'll notice again 1x, 1y. And here's how the syntax for plotting functions in Wolfram. Here's some examples of multivariate functions. So of course we can only visualize at most 3 dimensions. So you have x1, x2 as your x's and your y on the z-plane. This, by the way, could be a nice model of let's say, depression. You were once upon a time in love, and you remember vividly how you went out for dinner with your bae, and you were having 5 units of X1, fried chicken, 5 units of X2, gin and tonics, and at that point she dumped you. And from that point onwards, forever in your life, whenever you see a combination of 5 chickens, 5 G&Ts, you get depressed. Any combination of fried chicken and gin and tonics that's as far away as possible from 5 makes you very happy. This could be the surface plot of a utility function where somebody consumes two goods, x1, x2, as complements in a one-to-one ratio. So again, the point here is you have several x's, one y, Rn to R. Some example of a contrast between explicit functions and implicit functions. Here you're given a function y is equal to 3x4, so you can see that I can isolate y literally in terms of x's. Now here's a function x squared plus y squared is equal to 9, and you're not going to be able to get a function of y in terms of x's. So many of you will say, wait a second, well, that doesn't make any sense. Why can't I rearrange this equation and I get y squared is 9 minus x squared, then take square roots and get the y is equal to square root of 9 minus x squared. The trouble with that is if you go back over here, you have to remember the definition of a function. With every point in the x's, there is assigned a unique number in the range, the y's. So this is a function because for any given x, there's only one value of y. But had you gone that way and found out y is equal to the square root of 9 minus x squared, but you remember the square root is coming pluses and minus. So technically, if you isolate this expression in terms of y only, you would get the plus and minus square root of n minus 9 minus x squared, which means that for every given value of x, there will be two values of y. So this, in some strict sense, is not a function, but rather a relationship. Right? Not a romantic one, but it's a relationship. So what you have here is that x and y's are being implicitly defined by each other. Right? They're kind of like once you move some x, the y has to move according to this relationship that you see over here. So this is an implicit function, meaning that the f of x, y, f big F, x, y is an implicit function. It doesn't isolate y's in terms of x's, nor x in terms of y's. It just somehow has an equation where y and x depend on each other implicitly. Of course, notice that nothing stops you from writing down an explicit function in terms of implicit. For example, I could have said y minus 3x to the power 4 is equal to 0 and call the left hand side an implicit function of x and y. So you can always go from explicit to implicit, but not necessarily the other way around. And then we'll see when we can do this. Here's another more complex implicit function. Just to give you a taste of what's coming up in grad school, we have a very simple macro model where you have the goods and money markets. The goods markets works like this. GDP is equal to consumption plus investment plus government spending plus net exports. And net exports in turn are exports minus imports. So what you've done here is I brought consumption, investment, government spending to the left hand side. And now I subtract and add taxes. Of course, GDP minus consumption minus taxes is private savings. Taxes minus government spending is public savings, which must be equal to investment plus net exports. I'm going to assume that G is equal to T is equal to 0. Right? So that each of them is equal to 0. There's no government spending, there's no taxing. This is a pure, I don't know, anarchy over here. Right? Libertarian to the core. And so with that, public savings goes away, taxes goes away, and that means that the private savings of this economy, which of course by definition now has to equal total savings of the economy, the total savings of the economy must be equal to domestic investment plus net exports. But net exports are exports minus imports, and if I rearrange, I get an equation that says total savings plus total imports must be equal to investment plus exports. Cash inflows must be equal to cash outflows. In the money market, demand for money must be equal to supply of money. And by the way, if you for any MFEs or for that matter MAs, if you want, let's say, a reasonably short summary of how an economy works, slides, notes, and an Excel model that simulates a macro model, pretty well actually, you can contact me by email. I'll send it to you. Let's dig a bit deeper. 2 seconds ago, you said the goods market has savings plus imports must be equal to investment plus exports. But now in some courses, if you actually look at, for example, Barrow's intermediate macro textbook, he'll give you specific equations or graphs of savings and so forth. But in grad school, we don't do that, because it's unless you have data, it's kind of hard to know what the exact equation of savings, imports, investment, exports are. So why not do implicit functions? Let's claim that savings is a function ultimately of GDP, which is reasonable, higher incomes, higher savings, and interest rates. And whatever this equation is, even though I don't know the exact equation, that's what's called implicit functions, it must have some properties that as income goes up, saving goes up, it goes up, but less than by a dollar, right? And as interest rates go up, savings go up. That's reasonably good. Imports. Surely they're a function of GDP. As you get richer, you import more. And as income goes up by $1, imports could also go up but by more than zero but less than $1. And let domestic investment be a function of interest rates. As interest rates rise, investment falls. And let's now pin down exports to a specific level. We now imagine that no matter what happens, exports are always exactly the same. So that gives you this model right here. Savings plus imports is equal to investment plus exports, according to these equations that you saw over here. In the money market, let's assume the demand for liquidity is proportional to GDP and inversely proportional to interest rates. That's exactly what you see here. And now let's assume that money supply is fixed. So therefore, in the money market, demand for money, liquidity, is equal to constant money supply. So you'll notice that this entire macro model is now completely implicitly defined. We don't know the exact equations, but we know that these are the two equations. There are two endogenous variables, GDP and interest rates, and there are two exogenous parameters, exports and money supply. And somehow down the road, we will have to know whether such a system has a solution and whether how will GDP, for example, and interest rates react to changes in quote unquote parameters. Even though I don't know the equations, you'll see how we do this. So one of the ways we're going to do this down the road is that you could take this macro model and you could restate it this way. So what I've done is I've brought all the right hand side terms to the left hand side, so the only numbered right side is the number 0. And now this allows me to state two implicit functions, f1, f2. They're both quote unquote behind the scenes involve the endogenous variables, GDP and interest rates, and the exogenous parameters, exports and money supply. So you'll see that this system consists of two implicit functions, and we will soon see how to know whether such a system has a solution and how to do comparative statics, i.e., how will GDP and interest rates react to changes in parameters. Now let's do continuity. So continuity means that if you take a pencil, you can draw a graph without ever lifting your pencil. And here's a formal definition, which I'll leave for you to read at your own leisure. But basically, what it says is to find out if a function is continuous, it has to be continuous at all values of x. In particular, it has to be continuous at, let's say, any arbitrary value of x called a. How do I check if the function is continuous at a? Intuitively, what I do is I wiggle a little bit. Point, 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 point. And for anytime I wiggle, right? So here's the value of a. Here's the value of the function at a, f of a. If I wiggle a little bit over here, I will pick up a value of x that is going to give me the value of the function at a plus the distance between a and x, which is delta. And now, as long as this difference is less than some arbitrarily chosen number, epsilon can be any number that's big or small. So typically what you're trying to see is if I choose this point right here and quote unquote I draw a circle of epsilon radius, is there a value of x that gives the value of function really close to where I was over here? Here you can see it does, right? Because give me a value of the function at a point A, give me a value of epsilon, which is right here. I am able to find an x reasonably close to this point A so that the difference between this and this is less than epsilon. Here I can't do this because the way this function is defined is it's right over here, but there's a hole here. And the function at this point, x is equal to 2, jumps over here. Intuitively, I now choose a value of epsilon, really small. Am I able to find a value of x so that the value of x gives me a function really close, right? So this is f of a. Can I find a value of x, right? Somewhere around here. So, sorry, here's a function of a. I want to draw a radius around here and see if I can have the value of x, the function of the value of x be as really close to this dot right here. Well, that's not true because there is no value of x close to this one where, it's the second I wiggle a little bit this way, I jump from here to over here, which is more than the radius epsilon. So I didn't say that very well, but I'm sorry, but I think you get the hang of it, right? So it has to be you have to be able to pick a very tiny number, and you have to be able to have the function quote unquote continue in the region over here. Some rules, which I'll just go through very quickly. These are not really that important, but the sum of continuous functions is continuous. Multiply them, they're also continuous. Divide them, they are, and composition are also continuous. You remember composition from the previous lectures, right? One-to-one and inverse functions. Again, we're sticking to univariate functions. One-to-one and inverse functions means the following: that for every value of x, there's a value. So here, for every value of x, there's a value of y. But does every value of y have a unique value of x? So here you can see that's true. Every value of y, there's a value of x, right? So this is one-to-one. This graph is drawn for only values of x bigger than 0, bigger than or equal to 0, which means y must be bigger than or equal to 0. So you will notice that for any given value of y bigger than or equal to 0, right, there's a unique value of x, which I've drawn for here. So you can invert the function and now express the x's in terms of y's. E to the power x from x minus infinity to plus infinity is also one-to-one. Every value of y has a unique value of x. Right? And this allows me to invert this. I'm jumping ahead, of course, because we haven't seen log functions yet. And now I've drawn the graph differently. And now you can see that here's a one-to-one function, right? So for every value of y, there's a unique value of x. This is not a one-to-one function because for any given value of y, there are two values of x's. And the same thing over here, there's not one-to-one because give me a value of y, and I can find multiple values of x's, 1, 2, and 3, 5 over here, right? So what's nice is that a function can only be inverted. The y's are currently expressed as x's, but can you express the x's in terms of y's? You can do so if the function is known to be one to if and only if it is one to one. And if this, what this means is if with two f's, it means that if you have an inverse, if the function has an inverse, it is one to one. If it's one to one, it has an inverse. And you can, by the way, calculate inverse functions in Wolfram alpha very easily. Power functions. Here's some examples of functions: power functions, rational functions, and polynomial functions. Pretty straightforward. Let's go to exponential functions. Exponential functions take the form that y, the variable, is equal to a number times a base raised to the power x. The base b has to be always a number greater than 1. You can see that if I choose a value of b, the base less than, which is negative, I'll end up working the y's at complex numbers. If I choose a base that's equal to 0, well, then I get y's will always be equal to 0. It's not a very interesting function. If the base is a number between 0 and 1, then you will notice that I can always get y's in terms of some number to the power a variable, which of course is then, so here's a number less than 1, bigger than 0, less than 1 to raise to the power some variable. But I can now raise this, I can re-express this 2 to the power minus w, redefine minus w as x, and now you have a base that's suddenly bigger than 1. And of course, if I set now a base equal to 1, all the values of y are always going to be equal to 1. So if you need to have something interesting, where the y's actually have a story to tell, you need to choose a base that's bigger than 1. Any value of b that's bigger than 1. The preferred base is, of course, you remember from undergrad, is e, and the exponent, the quote-unquote exponent, exponential function. E, of course, is the sum converges to this number right here. I was going to make a joke that you have to memorize this number for the exams, but that would not be a funny joke. And of course, you should also know that I could have gotten this e expression from this expression. So e to the power x is defined as the infinite sum of x to the power n divided by n factorial. That's n factorial right here. Of course, what I did over here was I set x is equal to 1, which of course gave me the value of e. A few more words about e. This is kind of important, especially for the MFE students. So you kind of remember that E has something to do with continuous compounding. Let's go a bit deeper. Pretend that you are on January 1st and you invest $1 at an annual interest rate of R, which is now compounded every period. By this I mean, let's say a year consists of one period. 1 year. And now I compound so I invested a principal. At the end of the period, take it out. And if I have a next period coming in, I would then reinvest the principal plus interest again. But since I only have one period, I have nothing. I have no. What I'll have at the end of all my periods is 1 plus r divided by 1 interest rate, right? Compound exactly once. This is exactly how much money I'll have at the end of the year. But now I have 2 periods a year. In each period, I'll have this much money, right? Because I've taken the interest rate and interest rate divided by 2 now. And now at the end of the year, of course, I'll have, since there are 2 periods, this times this, right? Which gives you this expression. Now, if I have 3 periods, at the end of each period, I'll have this much money. And at the end of the year, I'll have this thing raised to the power 3. But the same token, if I have m many periods, and now if I let the number of periods go to infinity, you can see what the pattern here was. Here's 1, 1, 1, 1, 1. Here's r divided by m, right? Raised to the power n. As I shoot off m off to infinity, I get e to the power r. And again, I could have gotten the value of e by subbing in r is equal to 1, which would have given this expression. So this is, if you look at this very carefully, what this is saying is E is equal to, if the interest rate is 100% per year, of how much money you would get at the end of the year if you invested $1 on January 1st, 100% annual interest rate compounded continuously, that $1 would give you 2.718 quote unquote dollars at the end of 1 year. The trouble now is that all this was in 1 year. Now, what you want to do is a little bit something different. Again, you invest $1 on January 1st. Again, the annual rate is R, and again, is you're compounding it every period, depending, of course, right, on the number of periods. You now have 1 year. The clock starts at 0. T is years, ends at 1. It's now divided into m merry periods. By definition, each period is of length 1 over m years. I now want to know how much money, if I invest at time 0, and now remember that I'm compounding every m periods, right? How much money will I have if I start the clock at time 0? How much money will I have after k periods, which could be 1, 2, 3, 4 months, or it could be 24 months, it could be any number, right? So again, how much money will I have after k periods have gone by? Well, if there are k periods, how much is that in years? Each period is 1 over m years. So k periods is going to be k divided by m, t years, right? So that's how many years have gone by. So now I want to know that in each period, intuitively, if you just hide this k for a second, in each period I'm making 1 plus r over m, right? Go back to the previous slide. I'm making 1 plus r divided by m. If that's how much getting in each period, how much will I get after k periods? Well, I raise this to the power k, right, because of k periods. But now the number of periods in a year goes off to infinity. So I'm slicing the year into thinner and thinner and thinner slices. As n goes off to infinity, I use this. But I remind myself that k is equal to m times t. But now if I re-express this like this becomes easy to do, because in the previous slide you saw that this was e to the power r. E to the power r raised to the power t is exactly what you have over here. Awesome. So basically what you have to do is, if you want to know how much money you have after k periods, measure time in years and e to the power r into time t. Now we look at DCFs a little bit differently. In a traditional DCF, time is discrete and measured in years. So you can see that money cash flows arrive at the end of each year, X0, X1, X2, and so forth. The present value, of course, is where R is the annual interest rate. Simply you discount like this. Everyone knows this, of course. But now what we do is we divide up the years into periods, right? And now instead of getting cash flows at the end of each year, I get cash flows at the end of each period. Well, once again, in each period, there's compounding going on, where what's now happening is in each period, I take the annual interest rate. If I have n periods, the periodic interest rate would then be R divided by n. So in the kth period, I would get xk dollars, which then be discounted at the rate 1 plus the periodic interest rate, which is R divided by n, raised to the power k number of periods. Now, the, the, the trick, of course, is what would actually happen if I now start to compound it continuously as opposed to every period. In that case, this expression will then go off to e to the power minus rt. This is for the previous slide, right? Because we know from the previous slide that 1 plus this thing, when you shoot off m periods off to infinity, becomes e to the power rt. So by that logic, you now have this equation over here. So this shows you how to discount cash flows when you're compounding continuously. Going back to exponential equations, functions, we of course know that if you use the base e, if you have y is equal to e to the power x, that gives you the log of y to the base e is equal to x. So this is very tricky sometimes to read. So basically what it's saying is, look, e to the power x is equal to y. E to the power x is equal to y. So when somebody says log of y to the base e is equal to x, it's really not saying anything more than saying, look, if I took e raised to the power x, I would get value of y. And since log to the base e is really important in calculus, we call them natural logs. They're not organic or they don't, right? They're just natural. So we use the symbol ln, as you know. So ln y is equal to x means e to the power x is equal to y. Here's some rules of logs, which I'm sure you've seen as an undergrad. Here's some examples. You should look them over, right? The biggest mistake that people make, of course, is thinking that the log is a linear operator. Log is not it's not like sums or derivatives or integrals or expectations. You can't pass them through brackets. So log of a sum is not the sum of the logs. So the log of a product is the sum of the logs. The log of a ratio is the difference of the logs and so forth. But this one, you can't do anything with this. And there's some examples over here. Let's do differential calculus. I'll start with one variable, and I'll make the distinction between derivatives and differentials. First, some limit theorems. So again, reminding you from undergrad that if you have a function of y in terms of x's, if somebody says that x is now shooting off to x0, then the limit of y would then be a plus bx0. If y is always equal to a constant, and even though x is going off to a constant, y is going to remain a constant. If y is always equal to x, shooting x off to x0 will make y equal to x0. And if this is the function, shooting x equal to x0 will simply mean y is going to shoot off to x0 to the power a. Now you have limits applied to multiple functions. Here, one function that goes off to L1 when you shoot x to x0, and a second function that goes off to L2 when you shoot x to x0. What's the limit of these two functions, a times y1 plus and minus b times y2? Well, lo and behold, is a times the limit of y1 plus and minus b times the limit of y2. Limit of two functions multiplied, where each of them has limits L1, L2, is simply the product, and courses work exactly the same way. What's the derivative of a univariate function? What you do is you take the value of x, to compute the value of the function at some value of x, and now what you do is you change x by some discrete amount, delta x. Take the value of the function, at x plus delta x, subtract the value of function at x, divide by delta x, and ask yourself what will the expression look like if you set the change of x off to 0. You, of course, remember that from undergrad, to do this, the function has to be continuous and quote-unquote differentiable, which means no kinks. Let me give an example of, let me try to derive the derivative of x squared from first principles. Right, so here's x, here's a function of x. So right now, at x, this is equal to x squared. I now change x by a tiny discrete amount. Right, so x now goes off and becomes x plus delta x. So what's the value of the function when x is equal to x plus delta x? So instead of x, now you put in x plus delta x. Well, now you have to square this, and that's the expression right here. I know that if I have to take derivatives, I have to compute the change in the function. So the change is the value of the function at the new value of x, subtract the value of the function at the initial value of x. When you simplify this expression, and you should do this, this line minus that line gives you this expression right here. And now when I take the change in f and divide by delta x, this delta x disappears, right? Comes right here. This delta x now becomes delta x. And now I can take the derivative is defined as the limit of this expression as you shoot off delta x off to 0. As you shoot delta x off to 0, you simply get 2x. And what that means is, at this point, right, the slope for a very tiny change in x is given by 2 times x. So this would be so delta f over delta x is the slope from between those 2 points. F prime x is the slope at that point. That's a very, now we look at slightly something different called differential. So what's happening here is you took x before, you had the value of function at x. You bumped up x by a tiny amount, delta x, and you found that the value of the function at this new point, x plus delta x. Here was the change in the function, which you know from the previous slide was 2x delta x plus delta x squared, and here is delta x right here. The slope over here is, of course, this thingy, vertical distance, divided by horizontal distance, which of course is 2x plus delta x. Now, you also remember that the derivative was 2x. So ask yourself, can I express this change in the function that you see over here, which by the way is exactly the change of the function that you see down here? Can I break it down in 2 parts as follows? Because f prime is the slope at this point, slope is rise over run. So what's this rise? What's the purple rise over the red run? The purple rise over the red run, of course, is your derivative 2x, right? This is the slope right here, 2x multiplied by the run, which is delta x. So this vertical distance, of course, is the slope right here, f prime x, multiplied by delta x. So what should be left over, of course, is the remaining part. And if I know this was the change in f initially, 2x delta x, of course, is coming from what I just said right now, the purple part, right? From the derivative of x times delta x. So the remainder, of course, must be delta x squared, this blue part right here. So the total change in f is decomposed in 2 parts. One part is the derivative of x multiplied by delta x. The second part, of course, the terms in delta x squared. It's very common, by the way, in mathematics to denote something like this. This is simply saying that in general, if you take any function, not just x squared, the total change in the function, right, because of a change in x, delta x, is always going to be equal to the derivative times delta x, that you can see included right here, plus terms that are in delta x squared or higher. As you now make delta x smaller, as you now make this distance come smaller, 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 what's going to happen is this blue distance, the delta x squared terms are going to become smaller, smaller, become practically 0, so that for all practical purposes, you're left with this purple part. So what you're saying is, if you make this delta x really tiny, what's the total change in the f function? The total change in the f function would then be the derivative multiplied by the dx. See, the delta f has changed df, the delta x has changed into dx. They'll always be equal to f prime x into dx. How can you use this? Well, here's how you use it. Given the function y is equal to x squared, I already know that f prime x is 2x. Imagine now that I change x a teeny tiny bit, and I wonder what the total change in the f function is going to be. So there's 2 ways to do it. You have a value of x to start with, you have a new value of x, and you wonder what the new change in the y value is going to be. You can either find the change in the y value using calculus, that's this right here, or you can do it the exact change. Let's see how to use it by calculus. Calculus tells us that the change in the y value is the change in the f function, which is found by the partial derivative of x, partial derivative of f times dx. So the partial is 2x into dx. If I began with x is equal to 1, and if I change x by 0.0001, that's 4 zeros and 1, then what's the change in the f function going to be? 2 times x, which is 2 times 1 is 2, into the change in x, which is 0.0001. When I multiply these two, I get, according to calculus, when you go from x is equal to 1 to 1.00001, the function changed by roughly 0.0002. That is pretty damn close to the exact change in the y in the function, because the exact change is take the new value of x and square it, which is 1.0001 squared, minus the old value of x squared. The exact change is this value right here, and you can see that we're off by a very tiny amount. So calculus works really well when the change in x, if you go to use calculus to compute the change in the f in any function, it works really well when the changes are as small as possible. And this is something that will be very important when we do optimization in our next, well, couple of lectures from now. So just some notation. If I have a function and if I differentiate once, I get the slope. If I differentiate again, I get the slope of the slope. And as long as the derivatives exist, I can keep going, going, going. So you can use this notation, right, as long as those successive derivatives exist. Some rules. You could, if you want, derive the following rules by using first principles. I've done some of them for you in the appendix. If you have some time, do take a look at them. So by first principles, I mean simply using this definition. Can you derive the following? So you should now see, of course, that this is your classic. The derivative of a sum is a sum of derivatives, or derivative of a difference is the difference of derivatives. This is the product rule, which I'm sure you remember from undergrad. That's the chain rule. Z is a function of y, but y is a function of x. When x changes, somebody wants to know what the change in z is going to be. So you have to first figure out the change in x on the change in y, and the change in y on the change in z. So intuitively, by the way, this is not easy to prove. As you can see in the appendix, extremely hard. The change in z due to a change in x says first find out the change in f due to a change in y, then multiply by the change in g due to change in x. But of course, g is y, so change in g over change in x, of course, is dy dx. Chain rule. This is, of course, the derivative of a ratio, which, of course, if you want to derive this in first principles, it requires using the product rule and a chain rule. And this is actually telling you that if the function is 1 to 1, then this expression must be true. I'll use this expression in the next lecture. I know it sounds silly right now, but you see it is extremely powerful in advanced applications. Let me give an illustration of the chain rule. Just one more time. Z is a function of y, let's say y squared, but y in turn is a function of x, let's say x squared plus 1. Somebody says, give me dz dx, and let's say you want to do it without the chain rule. Well, without the chain rule, what you'll have to do is you have to express z in terms of y. Yes, you know the equation is y squared. But now you know that y is given by another equation called gx. Y is equal to x squared plus 1. So stick in x squared plus 1, the whole thing squared. Expand this, and now if I differentiate dz with respect to x, I get this answer. I have been jumping ahead because to do this derivative, I had to tell you how to take the derivative of x to the power n. I haven't done that yet. I've only given you general rules. I haven't given you specific rules for what to do. Sorry, I get that back. I've only given you rules for x squared, if you go back, right? But I haven't given you rules for x to the power n, or for that matter, log x and so forth. I just gave you general rules. So now, I'm somewhat jumping ahead, so you know already that this is 4x cubed. This, of course, is 4x. By the chain rule, it says, to find the change in z due to a change in x, differentiate the f function with respect to y, and differentiate the g function, or y, with respect to x. So simply differentiating z with respect to y. So z with respect to y gives you 2y. Y with respect to x gives you 2x. So all I have to then do is 2y times 2x. But now I have to remind myself that y, of course, is x squared plus 1. When I stick that in, I get the exact same answer that you did over here. Right? Incidentally, I just want to sort of motivate you as to how lucky we are that we're not asking you to do things for first principles, because if somebody did actually want to ask, did want you to show that the derivative of x to the power n is n times x to the power n minus 1. How would you do it from first principles? Well, you would start with the basic function. You would increase x by a tiny amount, right? That would mean that you would have to find out what's the value of x plus delta x to the power n. For that, you would have to use the binomial theorem, because if you remember, the binomial theorem gives you how to expand expressions like a plus b to the power n, as you can see over here. So you need the binomial theorem to say, if I took a plus b raised to the power n, what would the resulting expression be? And it's not a bad idea because we need this line and Pascal's triangle in probability theory. Notice that a plus b to the power 0 is 1. Sorry, let me back up. Everyone knows Pascal's triangle, 1. So the edges are always 1. And the numbers in between are the sum of the ones on top. So you can see that 1 plus 1 is 2, 2 plus 1 is 3, 2 plus 1 is 3. The next one will be 3 plus 1 would then be 4 down here, etc., etc., etc. And if you kept going, you would notice that it would always follow these rules over here, which funnily enough correspond to a plus b to the power 0 is 1, a plus b to the power 1 is 1a plus 1b. Sorry, I forgot to make this one red. So you can see those are the coefficients of a and b. See 1 and 1, 1 and 1. If I now expand this, the coefficients of a squared, ab, b squared are 1, 2, 1. See 1, 2, 1. Now these are coefficients of a cubed, a squared b, ab squared, b cubed, 1, 3, 3, 1, 1, 3, 3, 1. And if you kept going, you will then find out this is the coefficient of a to the power, well, a to the power n, right? Etc., 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 etc. Which allows you to write down the expansion of a plus b to the power n in this form right here, where there's the definition of n choose I. Right? Coming back to what you were doing earlier, you already have fx, you know it's x to the power n. You knew what f of x plus delta x was, that's this creature right over here, minus f of x. And now what you notice is if I now work out the terms x to the power n are going to disappear. The first term in here is x to the power n, it's going to disappear. And what you're left, of course, is terms in n minus 1, and of course lower powers, but higher terms with delta x or higher. So what you of course have is change in f is nxn minus 1. Pull it out from here, delta x plus all other terms involving delta x squared or higher. I have to take, when I take derivatives, I have to divide by delta x. When I do so, this disappears. That becomes all terms of order delta x or higher. If I now take limits, all those terms in delta x or higher go away to 0. And I'm now left, of course, which you already know from undergrad, the derivative of xn is, of course, n xn minus 1. To see how deep this result is, or why life could be very unpleasant, is notice that this proof was based on this expansion, and that expansion was based on the binomial theorem. The binomial theorem is only valid for positive integers. So you could not have used this proof if you were given a value n that was not an integer, right? For that, for example, 3 over 2, or was a negative number. So if you want to see how to derive so oddly enough, and it's kind of interesting, you get the exact same formula even if n isn't an integer, even if it's a negative number or irrational number and so forth. And to see how to do this, I urge you to read this marvelous book, Basic Training in Mathematics. And I've learned one thing in grad school, what was thousands of years ago. Anyone who says basic training in mathematics, an elementary note on something is anything but elementary. It's something like Feynman's 6 easy pieces. It's anything but easy. And then he had the gall to write a book called 6 Not So Easy Pieces, which of course was living hell. Here are some specific rules for specific functions. If you differentiate a constant, 0. If you differentiate a number to the times x to the power n, we just did this, you get this. This is a number multiplied by a function raised to the power n. So this is kind of important. If you differentiate with respect to n, multiply the number times n, take away 1 from the power of that expression right here, and then multiply by the derivative of the function right here. Here's the derivative of an exponential function. It is the old expression multiplied with the derivative of the f function. Here's the derivative of a number times the log function, which is of course the derivative divided by the function originally. Let's actually now combine the chain rule and sort of show you how to use the chain rule and this rule together for a more advanced application. Z is a function of y, precisely 3y squared. Y is a function of w, 2w plus 5, and w is a function of x, square root of x. By using the chain rule, I want to find out the change in z due to a change in x. I recognize that z is a function of y is a function of w is a function of x. So one way to do this, well, some people find it easier. I find it easier to first carry out the differentiate the w with respect to the x, then y with respect to the w, and then finally the z with respect to z. Or you could just do first do dz dy, right? That's your first argument right there, dz dy. So that will be, of course, 6y from up there. Then dy dw, that will be dy dw is 2. And then, of course, dw dx, which, of course, is this the derivative of this. I now apply this rule up there, and I get this over here. And if I simplify, I get this thing here. If you did not want to use a chain rule, you would have had to do 3y squared, sub in the definition of y, which is 2w plus 5 squared, then again sub in the definition of x, and now I can use this rule over here, and I'll go slowly. 2 times 3 is 6. Take away 1 to the power, that gives you 2 minus 1 is 1. And now multiply by the derivative of this thing inside the brackets over here. And you get the exact same answer that you did over here. Let's do some applications of logs. You notice that many times econ papers, instead of plotting a time series of x versus time, they sometimes plot time series a log of x versus time. The question is, why would you want a plot of log of something against time? Well, here's an answer. Very quickly, do you think the S&P 500 total return spiked up over here by a lot? Yes or no? Most people would say yes because the graph seems to be quite steep over here. But that's actually not quite right because here's why. Before I get to growth rates, let me show you a very important relationship. Notice that here you have x and here you have log of 1 plus x. You can do this in Excel, by the way, or Wolfram. And you notice that when x is small, x tends to be quite close to log of 1 plus x. The two things are quite close to each other. Right? You can see about 10% or less. The two things are quite similar. This matters because if you want a graph to say something about whether things are growing fast or slow, why don't we look then at the definition of growth rates? Time can be discrete, 0, 1, 2, 3, 4, or continuous, just all numbers are the same. What's the growth rate if you have discrete time? So the growth rate is defined as, I'll go a bit slowly, growth rate, the change in x divided by the change in periods, the whole thing divided by what x was in the previous period. Well, because you're in discrete time, this is your change in x, xt minus 1. And the change in periods is how many periods have gone by? Well, you've gone by exactly 1 period, right? So t minus 1 is, of course, 1 period. So you'll be dividing by delta x divided by 1, which, of course, is delta x, divided by xt minus 1. With a little bit of rearrangement, I get this. And now notice that if I take 1 to the other side, I get 1 plus the growth rate is equal to, what's 1 plus growth rate is the value of x today, divide the value of x yesterday. Take logs of both sides. And now if the growth rates are small, we invoke our approximation. We know the log of 1 plus something small is that small thingy. So log of 1 plus g becomes approximately equal to g. So the growth rates for small growth rates is log of the value of x today, divide the value of x yesterday. But by the rules of logs, this expression then becomes, of course, log of x today minus log of x yesterday. And of course, divide by 1, of course, is trivially obvious. But if you think about this, this is nothing but the slope of the time series of log of x something against time. Because if you plot something in terms of logs, what's the slope between any one year? Log of x at time t minus the log of x in the previous period divided by 1. So looking at the slope of a time series of log of time against time gives you the growth rates. But while I'm at this, you might as well do the growth rates in continuous time. First time people see this, they get really thrown off. We know y is equal to log x. You really remember from undergrad that dy dx is, you can use the rules I showed you earlier, 1 over x. If I want to get the total change in y, so here's what's happening. X is changing, causing a change in y. I know the change in y over the change in x is 1 over x. But what if someone asked me for the total change in y? The total change in y is the change in x divided by x. But my friends, y is just a different word for log x. So if you told me the change in y was dx over x, you must have also meant the change in log x is equal to dx over x. So therefore, notice the analogy. In continuous time, you want the change in x over the change in time. So you want dx over dt. So x dot is notation in macro for dx uh, dx dt, and this is divided by x. Sorry. So what I've done is I've taken dx dt down here and brought x over here. This is the exact same expression, right? This one right here. All right. So if you actually notice, this is nothing but dx over x. Dx over x is nothing but the change in log x. So this should be d log x dt. So again, if I plot a time series of log x against time, the slope gives you the growth rate. So if somebody gives you this graph, anyone who says, oh, the S&P 500 returns were really growing really fast is not quite right, because the slopes only give you the change in x, not the growth rates. But if you plot log of something against time, then of course we have the growth rates of the growth rate of x, literally. Let's do elasticity. You know that if y depends on x, when x changes, it causes a change in y. You kind of remember that in elasticity is a percentage change in y over the percentage change in x. But of course, you remember well from Eco 101, you should never compute percentages the good old-fashioned way. By good old-fashioned way, I mean, if you ask an elementary school kid, they will tell you the percentage change in y is change in y over initial y. But you remember Eco 101, you can't divide by initial y because, well, then the percentage change from A to B would not be the same as B to A. So what you do here is you use arc elasticity. You divide by the average of y and you divide by the average of x. Rearrange, you get this. If I now take the change in x, bring these 2 points closer and closer together, I get the point elasticity, which means you take limits. The delta y delta x becomes dy dx. Average of two x's, average of two y's becomes just 1 point x and y. And this is your point elasticity. Now imagine I give you this function and I ask you to find out the percentage change in y divided the percentage change in x. I want you to find out the point elasticity. If you use this formula, you could do it. I urge you to do it. First do dy dx. Stick it in. Then multiply by x. Then divide by y. Simplify, simplify, simplify. It's going to take you a long time. One wonders if there's a faster way when you are asked to find elasticity of power functions. Yes, you already know that. I'll skip this algebra right here because I've showed this already. You know the change in log x is given by dx over x. Take a look at your point elasticity formula right here. I bring it down here. I rearrange. This is, of course, change in y over y, change in x over s. But change in x over x is change in log x. And of course, change in y over y is change in log y. So you could have, to find out the percentage change in y over percentage change in x, I would differentiate the log of y with respect to log of x. And I do that in the next slide. I have this equation, take logs of both sides. I now want to differentiate the log of y with respect to the log of x. So this is your dependent variable, differentiate the dependent with respect to independent variable, which is log x, and the answer is minus b. And so you will notice that when you give it such functions, this minus b is always the elasticity, is always a constant, hence why these things are always called constant elasticity functions. Let's do Taylor and Maclaurin series very quickly. This is beyond amazing, right? Because I wish I didn't have to talk so fast. The reason I have to talk fast is because if my lectures go on too long, my computer won't save, uh, possibly won't save the file, so you lose lots of work. So let's go a little bit slower here. Imagine that you are, as you know, not God. You're just a mortal human being. God knows that there's an equation out there in terms of x, and God knows the true equation: 6 plus 2x plus 3x squared plus 5x cubed, which I've drawn for you here. God knows this. You, sadly, are not God, and you have no idea what this function is. And just like something out of the Bible, God reveals clues about this function one by one by one. So the Almighty tells you first, listen, I will not tell you anything about the function except one thing only. The value of the function at time 0 is equal to 6. That's it. That's all God tells you. And based on the fact that the value of the function at 0 is equal to 6, you are then supposed to guess the shape of this function, the entire function, just by knowing one number. Think about how crazy that is. Right? Now God gives you a second clue. Not only do I know the value of the function at x is equal to 0, which is 6, I can tell you the slope at the point 0 is 2. Just using these two facts, I want you to find out the shape of the function. And God keeps going. God gives you a second derivative at this point 0, and then asks you to find out the shape of the function. Keeps going. Tells you the third derivative at this point 0. You get the point. So God could give you not only the value of the function at point 0, but could give the first derivative, second, third, fourth, fifth, sixth. And the question is, if you had these clues, could you progressively, one by one by one by one, find out the value of the function, of the complete function? So it shouldn't come as a surprise that when I was first given the value of the function at 0, that it was equal to 6, my best guess is that the function should be flat at 6. But when I'm told that the slope is equal to 2, I know it cannot be flat anymore. There has to be somewhat positive slope over here. When I'm told that slope is second derivative is 6, I know it should be accelerating over here. When I'm shown that the third derivative is 30, I'm shown that the acceleration must also be accelerating over here. So you can see that having some clues over here, not only should give, what Maclaurin did was something gangster. Not only does he actually tell you what the shape of the function is going to be over here, but from information at x is equal to 0, he extrapolates the entire shape of the function for all values of x. I mean, really, that's actually kind of cool. To show how you do this, I'm going to assume that even though you are a cockroach and you know nothing, God knows the true equation. You don't know anything except these clues right here. The one assumption you can make is that the function is polynomial, or rigorously speaking, what you want to do is you're going to use a polynomial to approximate the true function. You don't need to assume polynomials. If you have some time, you can watch this video written by the same guy who wrote the book Basic Training in Mathematics. Here's how it works. That's Maclaurin, by the way. All right. Here's the function. Let's assume that the function is a polynomial of order n. God told you the value of this function at the value x is equal to 0. Well, at f of 0, the function then boils down to a0. Therefore, a0, that first coefficient a0, is equal to the value of x. You know what? I'm very sorry, guys, but this should be f of 0. I should kill myself at this point. This should be 0, my bad, not x0. So I'll miss that one. Sorry, guys. So we know that the coefficient a0 is the value of the function at 0 divided by 0 factorial, which of course is 1. If you differentiate, the first term disappears. This then becomes a1. Those terms will now start involving x's, right? And now if you ask me, if you tell me, if you say, hey, find out the first derivative at 0, anything that involves 0 goes away, and you're left with, of course, a1. So a1 is the derivative at x is equal to 0 divided by 1 factorial, which of course is 1. When you differentiate one more time, this a1 disappears, and now you're left with 2a2, and now all these terms involving x's. And now if you tell me to evaluate the second derivative with x is equal to 0, all those terms disappear, and you're left with 2a2. And if you rearrange, you find out that the a2 coefficient, of course, is second derivative as 0 divided by 2 factorial. If you kept going like this, you would finally end up at the end, the last term, which has now been differentiated n times, which means now this will be x to the power n minus n, which is of course 0. And now you'll of course have a n, which is a n right here. Since you've been differentiating this n times, it'll be n minus 1, n minus 2, n minus 3, n minus 4, all the way to 2 and 1 times x to the power n minus n, which is of course x to the power 0 or 1. When I set x is equal to 0, I simply get an into n factorial. And if I rearrange, I get that the coefficient an should be equal to the nth derivative at x equals 0 divided by n factorial. So if I was going to try and approximate the true function by a polynomial function, I had to guess the values of the coefficients a0, a1, a2, a3, and so forth. Well, Maclaurin tells you a0, of course, is a function at 0. a1 is the derivative at 0. a2 is the derivative at 0. Second derivative at 0 divided by 2 factorials. a3 is the third derivative at 0 divided by 3 factorials. an is the nth derivative at 0 divided by n factorial. And so what it does is it sort of fits a polynomial function into as an approximation. So again, going back to our example, God gave us these clues, remember? And from these clues, if the first clue was, if God tells me, Ajaz, the value of the function at x is equal to 0 is 6, right? Then I have guessed that a0 is equal to 6. So that means right now, at this clue and only this clue, I can guess the function is flat at 6. When God comes along and gives me a second clue that the derivative at x is equal to 0 is plus 2, using what I saw earlier, I can now write down the function as a0 plus a1 times x. And now I say, aha, at this point, the function is 6 plus 2x. As progressively more and more clues come in, and as my polynomial starts to expand according to that formula Maclaurin series, you start to see that my fit becomes better and better and better and better. In fact, if you kept going, at some point it would fit the actual function, quote unquote, perfectly, if you took it off to infinity. So you can see how we start flat, then we have now a straight line, which of course is logical because God told you the slope at 0 was 2, then became a curve like this because now second derivative, of course, is 6, right, is positive, and so forth and so forth and so forth. All right. Taylor series says completely something different. Taylor series now says, once again, God knows the true function. That says a polynomial. And God gives you clues not about the value of the function at 0, but about the value of the function at x of 0. See? So God progressively tells you the value of the function at x0, the slope at x0, second derivative at x0, third, fourth, fifth, and so forth. With all these clues, can I, just knowing what these things are at x0, can I find the value of the function everywhere? Well, yes, you can. Here's how you do it. You start by realizing that what you want to do is you want to take information at x0 and guess the function and guess the value of the function at any other value of x far away. Let's say over here. Use information at x0 to know what the function looks like at x. The distance between x and x0, x minus x0 is theta. Here, theta is negative. Here, theta is positive. Now, notice that any x by rearrangement will always be equal to x0, where you have information, plus the number theta, which, as you now know, can be positive, 0, or negative. To show how the Taylor series works, consider a second-order polynomial. Right? So imagine that we have to guess that this is in fact the true function, and our job is to guess the values of a0, a1, a2, given information about the value of the function, first derivative, second derivative, etc., at x0. We know x is equal to x plus theta. Stick it in, and now this becomes a function of theta. See, if I expand this out, I now get a function that's all now in terms of theta, the variable, because as x changes, theta changes. So now you have a function in terms of theta. I'm going to play the same kind of trick that I did earlier. Here's g of theta, I've written down for you. What will actually happen when theta is equal to 0? When theta is equal to 0, you're looking at values of x which are now equal to x0. So again, you're now asking what's the value of the g function at the value x0. Subbing theta is equal to 0 makes now g0 now becomes equal to this. And now you know that this entire animal should be equal to g0 divided by 0 factorial. Just kind of done this on purpose. You'll see why. If I take the first derivative with respect to theta, that term goes 0, 0, 0. This now becomes a1 plus 2x0. That becomes 2a2 theta. And now if I evaluate this derivative at theta is equal to 0, the second term disappears. Now you get a1 plus 2x0 is equal to g, the first derivative at 0, which of course means that I can rearrange this and now express this way. So you can see what I'm trying to do. I'm trying to express this first three terms in terms of g0. I'm now trying to express this term inside the brackets in terms of g prime. And now if I differentiate one more time, I get that this is equal to 2a2. And of course, when I evaluate this at theta is equal to 0, I get 2a2. So I've shown that a2 is equal to g double prime divided by 2 factorial, because 2 is 2 factorial. So what you've done is you have shown that the first three terms are g0 divided by 0 factorial. This thing inside the brackets is first g prime divided by 1 factorial, and a2 is of course g double prime divided by 2 factorial. And now we play a trick. Do you remember how we had, now let's evaluate the function at x0. Then you will notice that that's of course when, if you're evaluating at x0, that means theta must be 0. That means now g function must evaluate 0. So evaluating f at x0 is the same as evaluating g at 0, which of course gives you f of x at 0. When you do the first derivative at x0, that's the evaluating g function's first derivative at 0. So you can see these two things must be equal. By the same token, these two things must be equal. So what we now have is g0, of course, is f of x at x0. G prime 0 is f of x at g prime 0 is f prime at x0. G double prime 0 is f double prime at x0. Beautiful. And so we have this expression right here. But I remember that theta was x minus x0. Stick those in, and voila, you have the information. I want to approximate a function by by a second order polynomial. I have to guess the coefficients a0, a1, a2. Well, a1 is the value of the function x0 divided by 0 factorial. Then this thing over here is, you can see that now what I have is f prime, sorry, you can see that a1 will be equal to, you'll have to rearrange this a little bit, of course, over here. So this entire, this entire expression is equal to this entire expression where the individual coefficients are given by simplifying those things out, right? So you'll have to work this out to isolate those things in terms of the x's and x squares. So I'll do an example in a few minutes. Incidentally, the real Taylor series was supposed to expand all the way to infinity. So what people do in practice is they keep going to a certain order k, and then of course leave a remainder. So for example, here's a true function, 1 over 1 plus x, plotted in blue over here. I'm going to expand around x is 0 is equal to 1 till the fourth order to see how good that expansion is. When here's f of the f function evaluated at 1, here's the first derivative evaluated at 1, etc., 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 etc. And now I form the Taylor series using these expressions over here. And now you can see that if I plot this Taylor series, the purple line, the two things are very close to each other. So you can see how as I start to expand more and more and more to higher terms, more than 4, I'll start getting more and more accurate. But it seems to, you can see how quickly we start to approximate the true function, which is why it's so popular in mathematics and physics. So here's a summary of Taylor and Maclaurin series. I think I should stop here because my 1 hour is up. Otherwise, and I'll continue with lecture C2.